So this is Beginning Ham Radio for July 8th, and Bruce Schaefer, AA7PB, is going to give us a talk about SWR, antenna tuners, and dummy loads.
So I'll put this contact information on the last slide as well. But Max suggested a good resource. I don't know if it's a coincidence or not, but the topic is nicely covered in a series of articles in the January-February issue of On the Air. Much of my content I got from other locations, but I think if you read those articles, you'll find consistent information. So the way I think about tonight's topic is its ideas, its equipment, and its activities. And some of you will appreciate the equipment the most because it's tangible and stuff that you may already have or could buy. And some will appreciate the activities that can use this equipment, including helping you make a better purchasing decision, helping you adjust what you purchase, help you troubleshoot when something goes wrong, and some of you may actually want to build stuff. The ideas get somewhat esoteric, so you're going to have to bear with me. I think I only have one formula, and you can ignore that formula when we get to it, but there will be some concepts to talk about. But along the way, I will introduce the equipment to try to keep it somewhat down to earth. So just like when we talked about antennas a few weeks ago, the first principle is energy transfer. Alternating current can create radio waves if you route it to something that serves as an antenna. But inevitably, some of the energy will be converted to heat, which you can consider lost energy because that wasn't your intention. Heat is not lost energy if you're trying to heat your house, but it is when you're trying to make radio waves. And so that will come up in a variety of ways as we talk about the concepts and the equipment. To understand how this equipment works, it helps to understand a little bit about impedance. Impedance is similar to resistance, but also includes the effect of capacitance and inductance. And it turns out, for fairly subtle reasons, an antenna that's not resonant imposes the equivalent of capacitance or inductance, which adds to the impedance using a slightly complex formula, which I will not bother you with. If you have a transceiver that is its final stage is at a particular impedance, and you use a transmission line that has that same characteristic impedance and an antenna that it has that impedance at its feed point at your desired frequency, then almost all the energy will get converted to radio waves. You'll still lose a little bit in the transmission line, and we'll talk about transmission line loss. But if you have an impedance mismatch, you will lose some energy. And as we'll see, your transceiver may also try to protect itself from the impedance mismatch by cutting back the amount of power it's actually producing. So there's two ways to lose if the impedances aren't right. But there are things you can do if they're not right, and we'll talk about that too. The thing that happens when you have an impedance mismatch is you get a reflection. In the ham radio world, almost all that reflection occurs where the feed line meets the antenna. If you accidentally bought 70 ohm coax and hooked it up to your transceiver, you get some reflection right there because your transceiver is almost certainly assuming 50 ohms. But that would be unusual. You'd normally be buying 50 ohm coax. But what would be less unusual is you might be using some sort of ladder line And that has a different characteristic impedance that I won't get into heavily, but there's ways of dealing with that. Why would anybody choose something that doesn't have 50 ohms? Because some of those alternatives have lower loss, and in some circumstances, you want to go ahead and use them for their lower loss and deal in another way with the impedance mismatch. When reflection occurs, that's not a disaster, because in a interesting way, when the energy gets back to the transceiver, it bounces again and heads back to the antenna. The problem is that every round trip incurs some loss due in the transmission line, that's because some of that energy in each round trip is converted into heat. And that loss increases at higher frequencies, and it also increases with longer transmission lines. You get kind of an irony. A principle of antennas that we talked about last time is try to get it up high. But to get an antenna up high is going to require a longer line, and it's going to increase your losses. And if you have an impedance mismatch, the losses will be greater for reasons because of those additional round trips. So why do we talk about standing wave ratios? It's because some physicists figured out that when a reflection occurs, you've now got two waves on your transmission line, one outgoing and shown in blue here, and the other one coming back is the reflected voltage or power. And those two sum together, and this particular one is the worst case, one of the two worst cases, where you have a short at the end, where the two conductors have touched each other rather than going to two different places on your antenna, and all the energy is reflected back. And you, in this particular case, we get 100, where the power back is equal to the power out, you get an infinite SWR, which is certainly a worst case. More commonly, you'll get 1.5 or more, maybe 4 to 1, and or maybe, and there's some interesting circumstances, you might get 15 to 1. Because of the way the formula works, it's on the screen, it will never be less than 1. When you put in various values of reflected power, which is P sub R, and transmitted power into this formula, try various examples. If you've got nothing better to do, you'll always get a number 1 or greater. So we don't, in an alternate universe, we wouldn't have to necessarily talk about SWR. We could just talk about the mismatch. And we could talk about the implications of the mismatch, as we'll do mostly today. In our universe, there are two reasons why we could talk about SWR. One is physicists enjoy talking about it because of the way they think about waves and waves summing together, et cetera. And there's a direct analog to how sound waves work and waves in water work, that if you start studying waves, it gets real interesting conceptually. But that's not our purpose here tonight. The other reason why it's so common in ham radio is it turns out it's pretty easy to measure. And so everybody, almost everybody, starts talking about the measurements they have of SWR. Doesn't really matter whether you understand it, as long as you understand that 1 is really good, and 2 might be okay, plenty okay in some circumstances, and 4 is probably going to cause your transmitter to cut back on the power. Some transmitters will even cut back at 1.5. Many different SWR meters. The one on the screen happens to be a picture of the one I own. It's pretty basic. It's an analog meter that actually has 2 needles that you can't quite see in this picture because they're both not activated, because I disconnected it and took a picture of it. But if I was actually transmitting, the forward power would be the needle that rises clockwise from the left, and the reflected power would be measured by a separate needle that would rise counterclockwise from the right. and you actually eyeball the intersection of those two needles and look at the red lines to figure out what your SWR is. This is an old school SWR meter. I bought it only 3 years ago, but it's not much different than one you might have bought 30 years ago. Nowadays, it's pretty easy to buy an SWR meter that's digital and may have other outputs available as well. So this is not an exhaustive example. So what could you use an SWR meter to do? One is to detect a fault. Like I mentioned, there could be two wires crossed somewhere in the line, or a disconnected or a loose connection. Either of those will cause the SWR to bounce way up. Some radios will also turn on an LED, maybe with an icon on it that indicates high SWR, and it's warning you that the radio has cut back its power to protect itself. Some radios include an SWR built in, and they vary in how accurate they are, but if it's built in, you don't have a strong need to go out and buy one. I thought one of my transceivers only had SWR built in for HF, but it turns out it also has it for VHF and UHF. So I have a slightly redundant SWR setup, but it's helpful because I have a couple of other radios that I can use it with that don't have a built-in SWR. Another thing you could use it for to be less common, unless you're really into antennas, is to understand how flat your antenna is when it comes to resonance. It's common for a commercial antenna to be resonant in the middle of its target band. So if you bought a 2-meter antenna, it's probably going to be resonant at about 146 megahertz. It's not going to be resonant at 144 or 148, but it might be not too far off when it comes to SWR. So if it's at 1.1 or 1.0 at 146, and it's at 1.3 at 144 and 148, also 1.3 at 148, you call that a flat antenna with nice bandwidth for that band. That's pretty common in a commercial antenna for 2 meters, may not be quite as common for 70 centimeters because that band actually is pretty wide, and it's harder to create an antenna that has low SWR all the way across the 70 centimeter band. A more common use for an SWR meter would be to trim an antenna if you're making your own. It's sort of like carpentry and tailoring. When in doubt, make it too big because you can always trim it. Don't start on the short side because it's really hard to deal with making something longer, although sometimes it's possible. And that could be because you're making something out of copper or wire. Could be a vertical antenna or a horizontal antenna. You could be trimming it yourself, or you might have bought a commercial antenna that out of the box was on the high part of the band and you want to trim it down to be, was on the low part of the band and you want to trim it down so that it is in the middle of the band or the high part of the band. It's also possible that the antenna you bought is, even though it's commercial, is adjustable. I have a UHF antenna that you can use for GRMS or for the 70 centimeter band. But when you switch back and forth, you're wise to retune it by adjusting the length of two of its elements. It's called a collinear antenna. So you actually have to adjust it in two places, towards the top and kind of towards the middle. And at each of those places, two pieces of aluminum intersect one inside the other, and they're held together with a, what do we call this? sort of like an automotive hose clamp, right? So it turns out a small hose clamp works pretty well to clamp these two together, and you loosen that with a flat screwdriver, and you can slide them back and forth. If you buy that antenna, do you absolutely have to have an antenna tuner or an SWR meter? No, because it comes with a little cheat sheet that tells you for various frequencies what these two lengths should be. But if you're not sure you got it right, or you're not completely trusting of the cheat sheet, you can use an SWR meter or an antenna analyzer to get it almost exactly right by going back and forth until it's right. Another way of adjusting some antennas is with a threaded mechanism. Some of you know that you can build an antenna out of copper tubing if you've got the right blowtorch for soldering. The first J-pole I built, I measured it as precisely as I thought I needed to, and it turned out not to be resonant where I wanted it to. So the second one I built based on a web page somewhere on the internet, and I put two brass machine screws in the two ends, the short part and the long part of the J-pole. And after I got it all soldered together, I put those screws in and I adjusted them back and forth until I got the resonant location where I wanted it to be. And if I did a lot of work in one part of the band, I could change that to be more optimal in that part of the band. And an SWR meter or an antenna analyzer would be the tool I would use. So let me take a pause and take questions before I talk about the next thing.
So Bruce, so the commercial antenna, you mentioned that there are measurements, but if you are building an antenna, for example, like a 2 meter or dual band, do you need something like an SWR meter for that?
Maybe. If you're building a J-pole, there are a variety of web pages that will allow you to put in a frequency, and it'll give you 2 or 3 or 4 dimensions that you need in order to make that J-pole just right. But maybe you didn't measure quite right, and you still want to test, know more precisely whether it's behaving, or maybe you don't quite trust that web page that you use for your measurements. So that would be a reason to have one of these instruments to help tune it further. Another thing, when you're doing antennas like dipoles, is there are some formulas that ought to be right, you would think, because it's all based on the speed of light, but the thickness of the wire or cable you use will affect the speed of light slightly. And so you have to adjust there's a formula for adjusting for velocity factor. But some people just do it experimentally. They make it long and they trim it until their antenna analyzer tells them they got it right. I've seen people do that at field day, and it works quite well in the field. Anybody else have additional thoughts or contrary thoughts about that?
I just had a different question.
Go ahead, Michael.
Did you get your answer, Lee? Yeah. So it was in my situation, I have 50 ohm coax coming from a VHF, UHF radio out to a commercial antenna. And the antenna is tuned for 2 meters, 70 centimeter. It seems like an SWR meter in that case, based on your explanation here, would be overkill, unless I was worried about having shorts or something like that.
Yeah, I wouldn't quite say overkill, but it might not be your third, fourth, or fifth investment. You might want to put it down at number 10 on your list of things to buy. Mm-hmm. If you're going with commercial stuff and you feel like you've got good tight connections and you don't have any water encroachment into your coax and things like that. And that's why a lot of hams are totally successful without buying this additional stuff. So let's go to the next page, but I can come back if questions occur to you on what we've already covered. So a simplistic view of an antenna analyzer is an SWR meter with a little transmitter, low power transmitter built in. And so you hook it up to a piece of coax in this case that's connected to an antenna, and you select a frequency. This is an old school SWR meter that has an analog adjustment and some buttons to choose your band. But it does have a little digital display that's not on in this picture. And it gives you a readout of SWR, and it also tells you the impedance. And there are two components of impedance. It gives you both the resistance and the reactance. And so it's a pretty useful thing. But if you already had an SWR meter, why would you need one of these? Well, it's fairly hard to use an SWR meter right at the feed point. And if you want to analyze the antenna itself, it's could be complicated to do that, because if you're like me, your main rig is in the house and there's a piece of coax running somewhere to the antenna. Maybe you haven't quite put up the antenna yet, but it's outdoors somewhere. You're getting ready to raise it. And how do you test it? Well, maybe you get a pair of FRS radios and get a helper, and the helper sits in your shack and watches the SWR meter, and you make your adjustments. But it's a lot easier if you have everything together right outside where you're fussing with your antenna. But there's another reason having to do with being a good ham, and that is if you're making all these adjustments on an active ham band, you are taking up a frequency that might be needed by somebody else, or you may be interfering with somebody you can't hear because you're still working on your antenna. So in the old days, you would call such a person a lid. That's slang for a bad behavior in ham radio, to be transmitting more than a few milliwatts while you're adjusting your antenna. So perhaps the most important benefit of an antenna analyzer when you're tuning an antenna or adjusting an antenna is cutting the watts back lower than a typical transceiver is capable of going. The transceiver I use most often is minimum 5 watts, and that's probably way too much for tuning an antenna. What would be another reason? In some circumstances, you want to know the two components of the impedance, and a typical SWR meter, at least the old school ones, don't give that information. These days, a lot of people are buying a very fancy gizmo called a nano VNA. 10, 20 years ago, a VNA was a big box that cost several $1,000s. VNA is short for Vector Network Analyzer. It can do lots of interesting things, one of which is to give you an SWR curve or an SWR reading and tell you some things about impedance. And there's a lot of other things it can do as well. And they tend to run 50 to 110 bucks, depending on the size of the screen and the quality of the screen. The only downside that I know of, well, one minor and one not quite so minor, is there's such a sophisticated instrument that you could spend a lot of time learning it before you got around to actually using it. While a antenna analyzer is a relatively simple beast. The other is to keep it small, not quite nano, but they call it nano. It has very small connectors, and so you'll need adapters to connect it to a typical antenna. Those are inexpensive, but still an additional complexity. Any questions about antenna analyzers? So let's get a little deeper into the theory. Ideally, you want a match between your transmitter and your feed line and between your feed line and your antenna. It's usually the latter that's at issue, but it could be an issue depending on what feed line you're using. The SWR is a measure of matching and tells you something about how much power is being reflected. And we're going to talk about feed line loss next. Because the feed line loss is never zero, it's nice to have a good match because of what I mentioned earlier, that any mismatch will cause some % of reflected power, which will have to make additional round trips before it gets to your antenna, and more energy will be turned into heat. And a good match will also allow your transmitter to operate at full power. One way to improve your match is to have your antenna operate at resonance. That's not the only way. There are actually, there's an antenna design that's intentionally non-resonant. We touched on that when we talked about antennas, and feel free to ask it during the advanced Q&A, but don't ask it right now. It'll take us way off topic. For now, we'll just assume that you're probably dealing with a traditional antenna where you want to get close to resonance, close to the frequencies that you're going to be using. Will that get you to exactly 50 ohms? Probably not. Most antennas don't have a characteristic resonant impedance of exactly 50. Might be 60, might be 70. Some horizontal antennas, the radiation resistance is proportional to how high. And ironically, if you raise it up higher, some antennas will have higher resistance, and that'll increase the mismatch. You can deal with that with an antenna tuner. There's also, in some cases, you can deal with a fixed transformer solution, which is basically a very simplistic antenna tuner. And so we'll talk about antenna tuners in a minute. So let's go on for a moment. Let's talk briefly about feed line loss. If for some strange reason you were using coax to feed direct current to another location, pretty much the entire center conductor would be used, and whatever resistance you would measure with a voltmeter of a multimeter would, it would still be proportional to length, but you would use the full center conductor to transmit the main thing, and the shield also comes into it, but let's pretend it doesn't for a moment. But if you put 60 cycle, which I don't think you'd ever intentionally do, less energy would go through the center, and more of it would be transferred. More of the current would travel near the surface of the conductor. And if you jumped up to 10 meters, you're not using very much of the center at all, but you're using a decent amount of the thickness of the wire. That's the green part in C here. And if you get up into the VHF band, and even more so in the UHF band, almost no current is traveling except on the skin of the copper. So a fatter center conductor will have a greater circumference of its skin and will be able to transfer more energy. A thinner one will have less. So this is a graphical way of describing a fairly complex situation called the skin effect, which is proportional to frequency. And if you look up in a table, I didn't paste the table into this slide set, a particular piece of coax that performs well on the 40 meter band may perform very poorly on the 6 meter band, and extremely bad on the 2 meter band, and be useless unless it's only 3 foot long on the UHF frequencies. You spend more money on a fatter cable, a higher quality cable, and because it's got a fatter center conductor, it will perform better on all frequencies, particularly on the VHF and UHF frequencies. I've used fairly skinny cable for UHF where my feed line was 15 feet. But when I get to 50 feet, I have to pay twice because I need more expensive cable and I need 50 feet of it. So keep your feed lines short and consider how much you can afford to spend on the quality and the thickness of your feed lines. The main reason I'm bringing it up here today is that a 1.8 to 1 SWR on the 2 meter band may be fine, even through 30 feet of cable. But a 1.8 on the 70 centimeter band, you're going to lose a lot more energy due to feed line loss. And so you're either going to want to get that SWR down by better tuning, or you're going to want to spend more money on cable. Questions about that? So this is a kind of a summary slide of what you've already heard me say. I'll just let you glance at that. If you have questions, speak up or put it in chat. I think Max is probably monitoring chat for me.
Yep, nothing in chat so far.
Okay. So let's talk about antenna tuners. Antenna tuners can be very valuable in spite of the fact that their name is a big lie. They do not tune antennas. You can tune antennas in the ways we've already talked about by adjusting their length and a few other techniques. But you don't tune an antenna with an antenna tuner. What you do is you adjust, you compensate for a impedance mismatch with an antenna tuner. It doesn't change the impedance of your antenna. It helps you match the non-50 ohms that your antenna is producing with the 50 ohms of your coax. It's common to have your antenna tuner at your radio. A big advantage of having it there is that it can convert the impedance mismatch to close to 50 ohms. And so the transmitter part of your transceiver will conclude that it's got a good match and it'll put out as much power as you told it to. Without that antenna tuner, it may decide to protect itself by cutting the power back by a third, a half, or 80 or 90%, depending on how far off you are. So having a good antenna tuner at your rig solves that problem. And some modern, slightly expensive transceivers have a built-in antenna tuner, and some of them are very automatic. You may have to push a button to tell it to tune at a new frequency, but after that, it will remember the tune that it figured out for you automatically and go to that adjustment automatically as long as you have it turned on. And so they're pretty cool. Automatic antenna tuners you can purchase separately. And there are two reasons to buy one separately. One is because your rig doesn't have one. And the other is because most external antenna tuners can adjust for a wider mismatch. So if you have a reason to have a high SWR, and there are some good reasons that we can get into in the Q&A later, but not quite right now, then a robust antenna tuner can deal with that high mismatch and still present 50 ohms to your transceiver, even if the built-in antenna tuner cannot. A couple other concepts that you can ignore for now, but I put them on a slide for completeness. If you have a reason to have an antenna that's shorter than a quarter wave, let's assume it's a traditional vertical antenna where it's simulating a half-wave dipole by having a counterpoise, which might be the roof of your car or it might be radials. It could be resonant if it was exactly a quarter wave, but if it's shorter than that, for esoteric physics reasons, it is equivalent to having a capacitor hooked up to your antenna. It adds capacitance to the circuit. But that capacitance can be canceled out with an inductor, and that's where the antenna tuner comes in. If you happen to have an antenna that's longer than a quarter wave, then it's imposing inductance, and an antenna tuner can deal with that by adding capacitance and cancel it out. Now, why would you have an antenna longer? Well, it may be that it's not longer in the middle of the band, but it is longer on one edge of the band, and it's too short on the other edge of the band, so an antenna tuner can bring it back into line. Why don't you hear about antenna tuners for VHF and UHF antennas? Because they're short. It's so easy to create an antenna for the 2 meter band that's resonant at 146 megahertz and close to resonant with low SWR for the rest. You don't need an antenna tuner. I tried to buy one because I put my first J-pole on the roof, and it was so dangerous to get it up there. I didn't want to go back up to take it down. I wanted to buy an antenna tuner after I discovered it wasn't a good match. Couldn't find one. Nobody sells one, or at least I couldn't find one, because it's so easy to fix a 2 meter antenna or buy a better one or adjust it like we talked about. And similar on UHF, that one that had those hose clamps was the UHF antenna that's adjustable. So it's a lot easier to adjust the antenna than to buy an antenna tuner. For high frequency, however, you typically want an antenna that will cover multiple bands, and it's very hard to have the actual physical antenna be anywhere close to resonant across multiple bands. So an antenna tuner it's much more common and much more useful for high frequency. Questions about this slide or anything previous?
I was just going to make a
By the way, the
comment.
picture at the top, sorry, I interrupted somebody. The picture at the top is a manual antenna tuner, and the one just below it is a modern digital one that if you push a button, it will figure out the adjustments it needs in capacitance and inductance, and then it will remember that. And it actually figures it out based on the signal it's receiving from your transmitter. So whoever was trying to answer a question, please come again.
That was Max. I was just going to mention that because I saw the picture of the manual tuner up there, and for our field day, we have a few members that love open wire line or ladder line just because of its low loss. And so we end up using the manual tuners because they accept that ladder line at the rear of the manual antenna tuner, and then that converts to coax, and it makes it very easy to tune and not have to worry so much about loss in coax.
Yeah, exactly. That there are people that basically don't worry too much about how resonant their antenna is. Instead, they invest in a robust antenna tuner, typically the manual one for the reasons you described, Max. And then they use ladder line because it's so low loss that even though they're losing something in each reflection, it's not very much with ladder line, especially in the HF bands that they're using. But let's talk about that. That's a segue. Where would you put the antenna tuner? It's easiest if you put it right next to your rig or have it built into your rig, because you can reach over and push a button or turn some knobs. But at least theoretically, that's the worst place to put it, except for the power, letting your transmitter transmit at full power. Any loss for the round trips we talked about before are not being helped by an antenna tuner sitting next to your rig. So you have three choices at that point. One is live with the loss, and the other is to get a transmission line that's extremely low loss. And ladder line in the HF bands is extremely low loss, and so people often choose to use ladder line and a robust antenna tuner right next to the rig to match the mismatch to the rig and not worry too much about the loss in the feed line because it's relatively low. But if you didn't have that situation, or you were operating at a frequency where there was more loss due to that skin effect, you could move your tuner closer to your antenna. In this example, a 300 ohm line, perhaps ladder line is, or a twin lead of some kind, but it's probably ladder line. Max, is some ladder line 300 ohm?
Yes, so 300 ohm is, I guess another name for that is twin line or twin lead. It's the kind that they used to use for TV antennas with little rabbit ears.
Oh, the old TV antennas were 300.
Yeah, so it's not as common anymore. So commercial ladder line that you can buy is 450 ohms, or at least that's what's on the label. And then a lot of people, if you make it yourself, you'll just make you'll use 2 wires with spreaders that you make out of wood or plastic, and that's typically 600 ohm.
Okay, so the number here in the middle of the slide, 300 ohm, if you're using ladder line, substitute 450 or 600, but you'll have the same idea that you might have 25 or 50 feet of that going straight up to your antenna, and then have a way of placing the tuner at that point, and then maybe it's another 50 to 150 feet to your rig to get it into a comfortable place in your house. But that can be coax because the tuner is transformed that impedance mismatch to approximately 50 ohms presented to that coax, and so you have a good match from your transmitter to your coax to your tuner, and your antenna is probably not going to be 300 ohms, but the reflection back and forth in that low loss ladder line won't matter nearly as much because it's relatively short and low loss. A typical dipole is probably going to be closer to 70 ohms, and a folded dipole, I think, gets up to higher impedance. So it's all in the details. So how would you have a tuner in the field? It would be probably be remotely controlled, so that's going to run up the cost. And you're going to need to probably have it protected from the weather, so that's going to be a complicating factor. But there are hams out there that they already invested in a tower, so they invest in a remote antenna tuner at the base of their tower, or at the base of where they have their feed line going up to a horizontal antenna, and they control it remotely. I've never seen this. Max, have you ever seen somebody with a remote antenna tuner?
I mean, I'm familiar with them. I've seen them in catalogs, but I actually have not seen any in use. But they are very nice and convenient.
Yeah, Fred raised his hand. Have you seen one, Fred?
Yeah, I saw several of those. So basically, you're going to see a remote antenna tuner on the random length antenna, for example. So if you look on Google, you're going to see those antenna tuners. They're hidden under the eave of the the roof, and then you have a wire going out, because those antenna, they are not resonant. So you don't want to feed them with either a ladder line or a coax, because you're going to have too much losses on the coax. So you put a remote antenna tuner under the eave of your roof, and then you have your wire going into a tree or something like that. And also, if you look at a flagpole antenna, the antenna that are used by people who have a problem with the HOA, they just put a flagpole. It's a vertical antenna, and they have an antenna tuner at the base, because the same thing. The thing is 27 or 43 foot tall, and it's a non-resonant antenna. So if you feed that directly and you have your tuner next to your radio, you have too much losses in the coax. So you need to have a remote antenna tuner for that.
Good. That's good. Good learning on my part. I just noticed that we're behind schedule, so let's see how many more slides I have before we go to the general Q&A. Oh yeah, we're down to the last slide. Good. Max asked me to also cover dummy load. Dummy load conceptually is the world's worst antenna. It intentionally does not produce radio frequency. It produces infrared or heat. And why would you need one? Because you're troubleshooting a situation where it's going to take a while and you may need to be using significant wattage to really get to the bottom of the problem. And you don't want to be violating FCC rules or more importantly, interfering with other ham radio operators, especially if your equipment isn't working, you don't even know whether they're on frequency, you can't give your call sign to stay legal. So you essentially buy a resistor that pretends to be an antenna, but produces only heat. The challenge here is that if you're putting out 50 to 100 watts, or in some configurations as high as 1500 watts, a typical resistor will burn out. So you have a couple of choices. You can put fins on it, and there are commercial dummy loads that have fins, as shown in the upper picture here. Or you put it in a bucket of oil, and you can either make your own. You can find those where you literally get a paint can and you mount a coax connector in the lid, and you put the resistor inside and you fill it full of I think the equivalent of mineral oil or maybe even cooking oil, and it absorbs enough of the energy. The can probably gets warm, but you can use it as a big heat sink. Or you can buy them. This is an old picture of when Heath sold them, but there are other manufacturers that will be happy to, I think including MFJ, will sell you a pre-built paint can full of oil with a resistor inside. So that's, I think, my last slide, except for the one that gives my contact information again. Happy to go back to any previous slide. Michael, you had a question?
So dummy loads is an area where I just don't, I don't have a grasp of how big a dummy load to get, whether you get an oil can version because it'll handle long time transmissions at high wattages, or can you get by with one of those little teeny tiny dummy loads? Because
the article on dummy loads in the issue of On the Air that I mentioned makes a couple good points about that. You have to read the fine print. There's typically two specs. One is kind of the instantaneous wattage that they'll take. If you hooked it up to a Morse code key and you press down and made a dash and then let up and let it cool down for a couple of minutes, it might absorb 100 watts and be tiny. But if you locked your push to talk on your desktop mic and left it on for 5 minutes, it would burn out because it couldn't dissipate that heat. So there's another one about continuous dissipation that you would want to read for that situation. So it depends on what you're trying to troubleshoot and whether you can do something equivalent to a DID or a dash to troubleshoot the situation, and whether you need to transmit for quite a few seconds, in which case you're going to need a bigger dummy load with bigger fins or a can full of oil. I bet you Fred or Max can give a better answer.
I'm going to take it. Max didn't take it, the
Yeah.
mic. Yeah, I mean, you said everything. So it all depends how much power you're transmitting and for how long you're transmitting that power. And also you need to be careful of the duty cycle. So for example, if you transmit, if you press on the push to talk on SSB and you don't talk into your microphone, you're not transmitting any, almost any power. If you're transmitting an FM, you're gonna have 100% duty cycle, meaning you are transmitting really 100 watts. So that's something you need to consider also.
Yeah, so it'd be mode dependent. Yeah, good point.
The different modes you were talking about were
Single sideband versus FM.
Okay.
In Morse code would be the same. Key down would be 100% power. Key up would be 0. AM would, if nobody uses it anymore, but would be fairly similar to FM.
And those are issues for when you go HF, because VHF and UHF don't really work sideband. So they just work FM mostly.
Yeah, that would be the simple statement, although there are people that have figured out how to get longer distances on VHF using single sideband. So for those folks, the mode would be relevant.
There was a question in the chat about Bollins. These are balanced to unbalanced. And he's asking, he has one that has a switch with a 4-to-1 and a 1-to-1. And we wanted to just know what the difference between those two are.
Okay, I'll give the first pass on that. The original reason for a balun is to match a unbalanced antenna to a balanced, or more commonly a balanced antenna to unbalanced. The classic example for balance would be a dipole, and unbalanced would be a piece of coax. And there are a couple of important reasons why you want a balun in order to take care of the fact you're going from balanced antenna to an unbalanced feed line. But some smart person said, well, if I'm going to go to all the trouble of creating one of those, I could make it a little bit fancier by including the equivalent of a transformer in it. So if the antenna design that I chose, let's say it's a full dipole, I'm not certain, but let me pretend that it's 300 ohms. I could have a 6-to-1 transformer built into my balun so that I could match that 300 ohm antenna with a 50 ohm coax, and I solved two problems in one little box. There are other situations where you're going from unbalanced to unbalanced. There are antennas that are fundamentally unbalanced, like NFED, and the coax is unbalanced. And normally you would say, well, then I don't need anything. But if you still need to transform the impedance mismatch, then the slang term for that transformer is un, for unbalanced to unbalanced, because it's transforming the voltage and therefore the impedance, so that you can use a feed line that has a completely different impedance than the feed point of that antenna. What did I leave out?
I think that's a pretty good description.
Got close? Okay, yeah. Good. I've been listening to other people answer this question. I finally got the story close.
Thank you. It demystifies it for me. Appreciate it.
So Max, before you said that during field day, there's people, they like to use an antenna tuner, a manual antenna tuner, because it can take the 400 ohm window line. If you open one of those antenna tuner, if you look inside, you're going to see that to go from the window line to the rest of the tuner, they use a 4-to-1 balun. So if you take an automatic antenna tuner and you put on the back, you put a 4-to-1 balun with on one end, on one side, your 400 ohm feed line, and on the other end, your coax, you can just directly go into the tuner and use that automatic antenna tuner.
So you could argue that if you had a manual antenna tuner with a coax input, you could add that 4-to-1 and you would have what you needed, 2 boxes, or you could combine them into one box by paying more money. But in the case you're talking about, you're wanting to use an automatic antenna tuner. and then used a balun on the outside to match the 300 ohms, right?
Yeah.
Yeah, and Fred, that's technically what we do. However, we do use antennas that are cut, for example, like for 40 meters, and we use that on 20 and 15 meters also. So if we were only going to use it on the one band that the antenna is cut for, then we would just use a 4-to-1. It's the manual antenna tuner addition of the being able to adjust the capacitance reactance. We can then use it on other bands.
But that's you can do the same thing with the automatic antenna tuner. It's going to work the same way. It's just the only difference you have between those old tuners and the new one is the old tuner, they have a 4-to-1 transformer inside, and that's it. But the rest is capacitor and inductance, and the automatic antenna tuner is going to tune that thing way faster than manual one.
Yeah, no, that makes sense. Actually, I haven't tried that. I'll have to take out my 4-to-1 and balun and give it a try. Yeah, because we're using Elecraft radios, so they do have a fairly wide tuning range.
So I have just a dumb question, because I haven't really thought about baluns ever before. You're talking about a ratio like 4-to-1 or 3-to-1 or whatever these baluns are. So is that a ratio between the impedance on one side and the impedance on the other side, and you're trying to get them close to each other?
Yes.
Yeah.
So if you have a 450 ohm something and you're connected to a 50 ohm something, wouldn't you?
It's a 9-to-1.
Yeah.
So but you're talking about you can use a 4-to-1 because the tuner itself will also be able to deal with the rest of that mismatch?
Yeah.
Right.
Okay.
Yeah.
Okay.
So it's to bring it
and
closer.
Close enough so you can tune
the
it.
way I think about it, Michael, is a long time ago, somebody explained to me that if I wanted to transform AC voltage, I could get any other voltage I wanted by winding the primary and the secondary in the proper ratio.
Right.
But what I didn't understand until more recently is buried in the math of how a transformer works in converting voltage, and the fact that it also has the opposite effect on current. If you do the math, it's also having that effect on the impedance.
Because I
Because
understood
the
about AC
impedance is the ratio of the voltage to the current.
I sort of understand how AC transformers work, so now I just was making sure that when you said 4-to-1, it just got you in the ballpark, and then you could deal with it.
Yeah.
The second stage. Okay.
So one of the thing I would like to add about impedance matching is, so let's say you put a dipole, and like Bruce said before, the height of the dipole is going to determine your impedance. So let's say you put your dipole at 30 foot. You're going to measure your antenna with the SWR meter, and you're going to try to trim that antenna to the right length. So you're going to have a dip into your SWR somewhere, but don't expect to have a 1-to-1 SWR, because the characteristic impedance of that dipole at that height, it's going to be probably 100 ohms. So you're never going to have a 1-to-1 SWR. So now let's say so you put your dipole at some height, and you have a 75 or around 70, 80 ohm impedance. If you take Cat5, the TV antenna, it's 75 ohm. You can go all the way down to your almost to your shack, and you can directly connect that thing to a 50 ohm coax. And so what I'm trying to say is the reflected power will start where there is a mismatch. So if you put a coax 50 ohm from your radio to your antenna, the mismatch is going to be at the antenna. If you put 75 ohm coax all the way to your house, and then you have a 50 ohm from the outside of the house to the radio, the mismatch will be where the 50 ohm and the 75 ohm coax meet. So your losses will be way less, because you're going to have a shorter piece of 50 ohm coax than if you were going directly to the antenna. I don't know if I'm clear here.
No, that's a good point. And that's a clever way of violating the ham radio standard, is to say, well, just because we think we're 50 ohms is a standard doesn't mean the antenna is 50 ohms.
Yeah.
And if the feed point is matches a different type of coax, use that other coax and then do the final match closer to the rig.
So the thing is, the next stage is to do a little bit more math. Is to let's say you have your antenna is 100 ohm. You put a certain length of coax. Every time you're going to plug something to your antenna, you're going to transform the impedance. If you have an antenna and you put a 50 ohm coax, that's going to transform the impedance of your antenna. So then you can be clever and to put the right length of 75 ohm to bring that impedance to 50 ohm, and then you connect your 50 ohm coax with your 75 ohm coax, and you have a perfectly matching network from the radio to the antenna with no problems and no losses.
Yeah, you're right. That I did that in an emergency situation where I went and got a very esoteric piece of coax to act as my impedance match when on that same J-pole I was telling you about. But I guess the trick there is a combination of doing the math and then finding the right length of coax. And would you agree, Fred, that if the right number was a bit longer than the distance, you would just add some slack to your feed line in order to get the right length to get the match from the coax? I
didn't understand what you said just right here with the length.
Well, let me give you a concrete example. Let's say you decide you want to try this idea with using 70 ohm to do an impedance match and get it down to 50, and you run the numbers, and the length you need is 80 feet, or the equivalent in meters, but your feed point is only 50 feet from your rig. You could put 30 feet of slack on that 70 ohm cable and to get the solution.
Yeah, and so one of the things is ham radio operators, they dismiss the cheap coax 75 ohm coax cable you find at Home Depot. So first of all, they're mass produced. They're cheap. They're resistant to UV. They're resistant to water. I mean, they're pretty good cable, and they have a very low loss because those cable, especially on HF, because those cable they are used on UHF for TV. So they have a very, very low loss. So it's a good quality cable, with a very low loss, and it's cheap.
You're saying you could run just a longer length of this 75 ohm cable, and that would, I lost where it matches with the 50 ohm because it's done.
Oh, it's totally buried in the esoterics of wavelength and the capacitance and the inductance that is created by the impedance in the line. And so you do a whole, you can use Smith's chart, or you can do some complicated math, and it turns out that a length of coax will act as the equivalent of an unun. You build an unun out of a length of coax in this case by doing a bunch of math. Is that in the ballpark, Fred?
Mm-hmm. So you need to see every line you're going to use, coax or ladder line or anything, you need to see that as a network of capacitor and inductor. And you can take advantage of that capacitance and inductance to transform the impedance of your antenna.
Sounds like when I start doing HF, I'm going to have to learn a lot more.
Well, have to is strong. There are simple HF solutions. If you want to work the 20-meter band, you put up an antenna that's approximately 10 meters long, feed it in the middle. Or you buy one that somebody's cut already for you, and depending on how high you put it up, you may want to consider having a balun that also does a little transformation. But you can probably on 20 meters, you can deal with a certain amount of loss if the line isn't too long, and you feed it to your rig, and that HF rig may have a built-in tuner, and you get out and you make a bunch of contacts, so you're fine. But then you start raising the antenna higher in the air to make more contacts, and the impedance goes up, and then you scratch your head, say, well, now I've got a longer piece of line, and I've got more of a mismatch. So what do I do about that? But you don't have to worry about it on day one.
So one of the things I would like to add is don't build a dipole. Don't buy a dipole. Build it. A dipole is just a center point and two pieces of wire that are for 20 meters, for example, they're going to be 5 meter long. You don't need to buy that, because if you buy that, you're going to pay $100 for something that anyway you're going to have to build, because they're going to say, oh, connect that wire here, put that thing up in the tree, and now take your radio or your antenna analyzer or your SWR meter and cut the end of that antenna until it matches. So basically you are paying $100 and something to build. Anyway, you're going to build it. So why pay?
Right. So you're basically saying for $100 you can get $25 worth of parts and then build it, or you can go out and buy the $25 worth of parts and build it.
My problem is not at the length of the antenna, it's having the antenna up somewhere that other folks in my family can see it. So that's another issue altogether.
Yeah.
Yeah,
or
but
your
that's
neighbor.
something you cannot buy from the store.
I understand. That's why I'm interested in your Monday topic.
And by the way, go vertical.
Yeah. Oh, because I've heard that vertical is not as good for HF because of the polarization. Most people are running horizontal antennas.
So the polarization is important for VHF, UHF, because you do line of sight contacts.
Mm-hmm.
And so basically I'm going to be here, you're going to be on the hill over there, and we can't see each other. And if you have a different polarization, you lose 20 dB minimum. So on HF, that's not true anymore, because your signal is going to bounce off of the ionosphere, and when it's going to come down, the polarization is going to be all screwed up and mixed up and all, you don't have that vertical or horizontal polarization anymore. So on HF, that doesn't matter, the polarization. So what matters on HF is the takeoff angle of your signal. So you want to have an antenna that radiates horizontally as far as possible. So like that, you're gonna get your first bounce pretty far away from where you are, and you can make long distance contacts on HF by having a very low takeoff angle. So when you build antenna, that's what you are looking for, a very low takeoff angle. If you put a dipole, if the dipole is not high enough, if for the takeoff angle will be pretty high up in the sky, so you're going to send most of your signal vertically up instead of sending it far away.
If I can't get a dipole high enough, I should just go for a vertical then.
If you cannot get a dipole high enough, go for a vertical.
Wow.
And so you might wonder why people put up horizontal. I think it's for two reasons. One is it's kind of a tradition of the ham radio to do that. And the other is for some bands, like the 80 meter band, it's a pretty long vertical distance to go, and it may be easier to find two locations to run it horizontal, even though your takeoff angle will be suboptimal. At least you got an antenna.
Oh, I have a counter argument on that.
Could I just ask, on a vertical antenna, does it actually have to be a half wave in length physically, or can you use those like coiled, whatever they call those? The wire is sorry?
The cap hats?
I don't know if that's what the term is, but
Yeah.
inside the antenna, there's those coils,
loading coil.
Loading coils.
Okay.
Yeah.
Yes, and yes, and yes. So, so first of all, it's not a half wavelength. It's going to be a quarter wavelength. So it's going to be a shorter. Then you can load your antenna with a loading coil to make it shorter. So on 20 meter, it doesn't make much sense because it's only 5 meter. It's a 15 feet. It's not that high, even though you can use a loading coil. But then the loading coil will become more important when you want to have your antenna working on 40 meters or your antenna working on 80 meters. The capacitive hat, it's a way also to shorten your antenna. So if you have, I don't know the numbers exactly, but if you have so let's say your 5 meter is too high, you want to put only 3 meters or 4 meters, you can put that 3 meter antenna and put a capacitive hat on top of your antenna, and it's going to be shorter. And then to answer to what Bruce said, dipole antenna is the basic antenna. It's the antenna that is the base for any other antenna. And that's why a lot of ham are using those antenna. It's, the first thing you put up, it's a dipole, and the first thing they teach you is it's a dipole. But then the problem on 80 meters. So 80 meters, if you want to have an antenna that go far away, you need to put your antenna at minimum, really minimum 40 meters all the way up to 80 meters high. So I don't know any trees around here that are 80 meter high or even 70 meter high. It's impossible to put an antenna that high. So that's why a lot of people who are doing DX, they want to do DX on 80 meters. They cannot put an antenna high enough. They cannot put a Yagi on 80 meters because they are huge. So what they do is they go vertical, and if they can. And what they do is they use either a tuner at the base of the antenna, or they put a loading coil somewhere on that antenna to shorten the antenna.
So the loading coil becomes the equivalent of an unknown, but the physics is completely different.
The loading coil, what you want to put that loading coil somewhere in the middle of the antenna, not at the base of the antenna.
Oh, not at the base. Okay.
It's not. It's going to be more efficient if you put that. The farther away from the feed point, the better it's gonna be. But also, it's antenna is all about compromises, because the farther away you're going to put it, the bigger it's going to be in diameter, in size, and weight. So you need to find some good. But even at the base of the antenna, that's going to work.
So Max, did you want to open it up to other types of questions?
Yeah, and I want to thank you very much, Bruce, for a great presentation. If anybody has any questions on ham radio, I don't see any new questions in the chat, but I have one question for Fred. So for your field day, you actually used multiplexers, is that right?
We use a duplexer so we had two antennas. So we use a duplexer for the 80 and 40 meter antenna. That's the antenna I built. And then we're using a triplexer for the Mosley we had, which is a 10, 15, and 20 meters. And but you need to also to have a bandpass filters. You cannot use the diplexer or triplexer without the bandpass filter.
Okay. And did you feed those all with coax?
Yeah.
Okay.
The 80 meter, 40 meter antenna was fed with coax. It was pretty far away, so we had I think the total length was 300 feet. So, but what I did is I put a 75 ohm coax from the antenna. I put 60 foot of a 75 ohm coax to go kind of the antenna down, and then we just directly connected the LMR 400 of 50 ohm coax to that 75 ohm coax, and at the feed point there we kind of had a pretty good SWR. It was below 2. And the antenna was resonant almost flat on the entire 80 meter band from 3.5 to 3.9, I think 3.8 or 2.9. So we could work CW and phone without using a tuner, basically.
Nice. But then that's pretty unusual, because most 80 meter antennas have a hard time covering all 80 meters, because that's a pretty broad
yeah, I worked
band.
a lot to
Yeah.
it took me a lot of experimentation to build that antenna.
Nice.
But I don't know, if you pay enough, I can give you the schematics.
That'd be awesome. Now, is it possible to feed to use ladder line if you're going to use a multiplexer or diplexer?
No, you're going to have coax.
Okay.
And you cannot use a tuner either. So you need to have an antenna that are resonant.
Okay.
You cannot, if you go to your antenna, you cannot have someone. You cannot have, you cannot use the tuner to tune an antenna that is completely out of band. It won't work.
So even the automatic antenna tuner at the radio?
So they all brought their, old manual tuner because, we kind of like to use those things. And then they discovered that with the 80 and 40 meter, the SWR was, with the 300 foot of coax, it was, 1.2, somewhere, around 1.2. And they say, okay, they just at some point I saw them, they were disconnecting everything, putting the antenna directly at the radio, and just hit the automatic tune on the radio and use the internal tuner.
Well, that's great. One less thing to bring.
Yeah, it's also a pain to use those, especially when when you're if you're running, that's fine because you tune your thing and then you call CQ. But when you are doing a search and pounce, you need to retune that thing every time, especially if you want to do work on 80 meters, because the antenna, usually they have a pretty narrow bandwidth on 80 meters. So to retune that thing every time with a manual tuner is kind of a pain.
Yeah. Well, thank you. Any other questions?
I can just ask any old question I feel like, because I'm in a quandary about coax connectors. So I made my own cable feed line. It's RG213, and I used UHF connectors, PL259 and SO239 connectors. And recently I was watching, a YouTube Elmer talk about N-type connectors and saying that N-type connectors are much better than UHF connectors. And so I was just wondering, does it make sense to me? Because I've removed my antenna because my house is getting painted, and I have time where I have it all taken apart, and I could just cut off those UHF connectors and put N-type on. Everybody's nodding their head, but my radio has UHF, putting SO239 on the back, and the antenna is SO239. So am I still better off getting all in the rest of the way?
I can answer that question if you want.
Sure.
So if you first of all, if you are working on VHF or UHF, especially on UHF, there is chances the connector they're going to be type N connectors, not SO239. Or you need to ask for SO239. And like Bruce said before, it's just it's historical. People, they have used those connectors forever, and they like to use those connectors, and they use those connectors. And that's something that I think is US specific, because I come from Europe, and in France or in UK, every time they put a connector outside their house, they use type N, because type N, they are waterproof. They're
That's a
better
gasket.
connector. They're better connector. They do a better match. So on HF, it is, you know, the better match is not that important on HF, but it becomes important on VHF, UHF. And the connector, they're waterproof. So they just go on the antenna, they plug their connector, and they're done. Here we plug the connector, and then we put that plastic wrap around, and then we put that tape, etc., etc. And when you are putting your antenna and you don't touch that for the next 10 years, that's fine. But if you are doing experimentation, you want to connect, change things, you want to reconnect, disconnect, and connect, disconnect, and every time you have to peel off that crap, and takes time. It's leave that gooey thing around your connectors, and especially if you put a silicone grease, it's even worse. So that's why the people in Europe, they're using way more type N connector than here in the US. And the thing is, they're more expensive. That's one of the problem also.
Michael, I've started to convert. I made some mistakes early on. My surge protectors for my antennas are all but one of them is UHF, and from now on I'm only going to buy in. But to deal with that, since I make my own cables, I create hybrid cables that have N on one end and UHF on the end.
That's exactly what I was going to do, is cut off one side and have N on one end. And I was wondering, is that crazy or not? It sounds like it isn't. And then get an end lightning arrestor.
Right.
So, and any advice I give to someone who wants to make their own cable, use a crimp, don't solder.
That's okay. Well, it's crimp and solder, right? It's both.
So you solder the
connector.
center tip, and then you crimp the outside. Because
That's
the problem
exactly
is the problem is when you solder the outside, you need to. It's very hard to do without melting the inside insulator. And if you melt that thing even a little bit, you're going to change the impedance of your connector, and you're going to also introduce some more losses. So crimping, it's the way to go, and they're more solid also.
Cool.
Yeah, and with crimping, you can.
If you
go
buy
ahead,
a
Bruce.
commercial one, the shield is going to be crimped.
Yeah.
And you can get crimpers from Ham Radio Outlet, West Mountain Radio. They're not necessarily inexpensive, but if you're going to be making your own cables like Bruce mentioned that he does, you're going to end up saving a lot of money.
Oh, I've already got a crimp kit.
Okay.
Yeah, I made my own cables already. So
the only problem is you need to standardize on the cable and on connectors, because if you start, I'm going to use LMR 400 and then RG8X and then RG213, etc. None of those cables, they have the same size, and you need a connector specific for almost every of those cables, and then you end up having a ton of connectors, and you're always missing the one you need.
Right.
So what's your favorite cable? Is it the LMR 400?
Me?
Fred? Yeah.
No, they're too expensive. RG8.
Okay.
For low loss, I use RG8 because when everything is matching, I can go on the SimSmith and show you the when everything is matching and you have a good match. RG8X, you won't have more losses than with an LMR. The only difference is the LMR is going to cost you almost twice the price of the RG8.
You're talking primarily HF though, right?
Yeah, on HF.
Yeah.
On VHF, I don't do much because I don't have a radio with a SSB. So I just have my FM radio. I talk to the local repeaters here. And so I didn't do anything special. I'm using an headphone J-pole on the roof of my house. And I'm talking to people kind of far away because I can hit repeaters that are 150 miles away from where I am.
Wow.
That's
The
great.
only time I've gotten anywhere close to that is up on top of a mountain.
I am not on top of a mountain, but I am kind of on the side of a mountain, so I have a view on the entire bay, and I can hit repairs that are in the Sierra. So meaning in after Sacramento, I talk to people in Sacramento, and they say, "Oh, where are you?" I say in Redwood City, and they're what?
The comment, sort of a footnote to what Michael was asking about the how do you balance back and forth between the N and the UHF connectors? In the course of some routine inspections of emergency kits that are designed to be used by hams at local fire stations, I've encountered a couple of situations where they have a radio kit with UHF connectors and a socket in a wall-mounted box for the antenna that's using N connectors. And I've heard a report of at least one of those being damaged where somebody tries to screw them together. That's not what you want. So to have some adapters and, or double-ended cables or whatever in your kit, if you're roaming around to different installations, could be very functional. And otherwise, making cables can take some time.
Yeah, I don't think any professional field right now uses UHF connectors. They all use something else.
Yeah, I'm sure they felt they were doing the right thing by putting the N connectors in the box. It's just that the radio kit has UHF connector.
Yeah.
But it's probably 10 years old, so it needs to be updated. And
Roger, I ran into a case at a fire station where I think I tracked it down to the fact that in addition to the orange box that I had access to, there was another colored box in the fire station that only the firemen could use.
Mm-hmm.
And it had N connectors.
Mm-hmm. Yeah. Well, it's a funny situation. I suspect that part of the historical evolution of these things is that people could probably get Army surplus ones after the end of the war, and it became a widespread habit just because they were abundant. Bruce, do you have an impression on that?
Well, I have something consistent with that. Is we call them UHF connectors,
which is
because when they were originally introduced, 10 meters was ultra high frequency.
Yeah.
That's how far back they go.
Oh my goodness.
Now Fred suggested getting 75 ohm cable from a hardware store as an economical measure. Would you use instruments to measure empirically how well that's working if you're trying to mix and match things? You know what I'm talking about?
Yeah.
Take your nano VNA or whatever and try to assess, is my theory actually going to work?
So
before hooking the radio up to.
I'm going to tell you how I do that. So what I do is I take my antenna up and I measure I use an antenna analyzer, not a SWR meter, but an antenna analyzer that's going to give me all the numbers, the impedance of the antenna, but also the reactance of my antenna. And then I take those numbers and I use, let me be clear. I take the impedance at the antenna. Okay, so the problem is you need to calibrate your antenna analyzer with the length of cable you're going to use to measure at the antenna, because otherwise if you put a piece of coax from the antenna to your analyzer, you're analyzing the antenna at that point, so the antenna plus the cable. So you want to measure at the antenna. So when I have those numbers, I take a software that is called SimSmith. I plug those numbers into SimSmith. So basically my antenna analyzer, I save, I do a swipe, I save all those things, I put that file into SimSmith, and then what I do, I use the SimSmith to calculate the length of my coax, the 75 ohm. I see if I can do a good match or not. I see how much losses I'm going to get. So if I'm getting too much losses, for example, I'm going to try a new strategy or something different. So I'm with the SimSmith, what I'm doing is, seeing what kind of result I can get, and then SimSmith is going to give me the length of the coax or the 75 ohm coax I need to put. I cut that, plug on the antenna, and then I verify again with my antenna analyzer to see if I am in that ballpark number or if I am completely off.
So
And then I plug my 50 ohm. Sorry?
So you simulate to get your numbers. You get your numbers, then you do simulations to see what the correct length should be.
So you can take your pocket calculator and do all the math. It's quadratic equations to calculate that thing. So I am too lazy to do that. So I am software engineer, so I like to have software work for me.
Yeah, that's what it's for.
Yeah.
Roger and a Zeniac.
Cool. Well, I want to thank Bruce for his great presentation. I also want to thank Fred for joining us and helping out with a lot of the questions. I really appreciate it.
Oh, no problem.
This is 100% aces with me, I'll tell you. So.
And like somebody mentioned, the Monday meeting, I'm sure he's going to be talking about vertical antennas. So if you're interested in his take on vertical antennas, they have gotten a bad rap over the years, but I think he's going to dispel some of the myths about vertical antennas.
One of the biggest myths on vertical antenna, people are saying, oh, they're noisy. But I want to remind you guys that 95% of the noise on your radio is going to come from the common mode current you're going to have on your feed line and not from the antenna. So if you install your antenna correctly, you choke that thing correctly, and then your noise is going to go away.
That's a great point. Yeah, because noise, especially in crowded neighborhoods, is something that a lot of us hams have to kind of put up with or find out a way to deal with, to eliminate. Well, cool. I want to thank everybody for attending, and I'm just going to put up a slide with the upcoming future meeting topics. Next week, we're going to be talking about antenna restrictions, then Maidenhead grids and contesting, followed by operating in other countries and third-party traffic. If you have any future topics that you would like us to discuss, please email any questions, comments to me, Max at noltra.com. We want to make sure that this is going to benefit you guys, so give us some feedback. And again, appreciate Bruce, you and Fred joining.
You're welcome.
Cool.
Yeah, no problem.
Thanks.
Absolutely. Well, I'll see everybody on Monday if you have a chance. Otherwise, we'll put it up on YouTube just a couple days later.